Yeah, you can start, Skanda.
Yes, sir. We studied about mu law, sir. Like we again discussed about mu law and A law,
Uh,
and we started encoding, sir. We studied about encoding process, about code words and characters, and binary code and ternary codes, and also about line codes, unipolar
uh,
line code,
yeah, tell me
unipolar.
different types of line codes we have discussed, right?
Yes, sir. Unipolar non-return to zero and unipolar return to zero, and why it is non-return to zero and what it means and all we studied, sir, using waveforms.
Okay. Yeah, we were discussing about the different types of line codes, right? I said basically uh, NRZ and RZ, that is non-return to zero and return to zero. I said the return to zero uh, means the pulse will come back to zero before end of its duration, right? And non-return to zero means it will occupy for the entire duration of the pulse. This is what is non-return to zero. Yeah, I think from here, right? Uh, then I said the unipolar, polar, bipolar, and Manchester. Okay, these are the uh, main line coding techniques which are used, right? So I said in case of unipolar, non-return to zero, uh, the binary bit 0 will be represented by no pulse, and the binary data 1 will be represented by a pulse, okay, having amplitude plus a volts. This is NRZ, okay. In case of return to 0, binary bit 0 will be represented by no pulse, and 1 will be represented by a pulse having amplitude plus a volts, but it will come back to 0 after half of the bit duration. That is unipolar, right? So in case of polar, I said 0 will be represented by negative pulse, and binary data 1 will be represented by a positive pulse, isn't it? Yeah, so second one is the polar, this one, polar format. 0 will be represented by a negative pulse, and 1 will be represented by a positive pulse. Fine. So NRZ means I said it will occupy the entire bit duration. It will not come back to 0. Return to 0 means it will be uh, negative pulse for half the bit duration. Again, it will come back to 0 for the next half of the bit duration. That is what is return to 0. In case of bipolar, what I said, in case of bipolar, 0 will be represented by no pulse, and uh, 1 will be represented by alternate positive and negative pulses, right? So here, for this given data, first bit is 0, it will be represented by no pulse, and next bit is 1, it will be represented by a positive pulse. Actually, it is bipolar return to 0, it is. That is why for half the bit pulse, it come back to 0. Then next bit also is 1, so that will be represented by a negative pulse, having magnitude minus a volts. Okay, so this is what is bipolar. Okay, bipolar return to 0 it is. See, next 0 is there, no pulse. Next 1 is there. So previous one was represented by negative pulse. Now this one will be represented by a positive pulse. Okay. The next two bits are 0, 0. That is why it is represented by no pulse. And then the last bit is 1. So it will be represented by a negative pulse because the previous bit 1 is represented by a positive pulse. Hope understood this point. This is bipolar. Okay, bipolar means 0 represented by no pulse, and 1 will be represented by alternate positive and negative pulses. Yeah, next one is the split phase or Manchester code, I said, right? So here, in case of Manchester code, binary data 0 will be represented by a negative pulse for half of the bit duration, and another half of the bit duration, it will be represented by a positive pulse. Okay, so if I consider this is my bit duration, okay, TB, then for the first bit is my binary data 0, so it will be represented by what? Half of the bit duration by negative pulse, another half of the bit duration by positive pulse. So next is 1. So binary data 1 will be represented by a positive pulse for half the bit duration. For another half the bit duration, it will be represented by negative pulse. Okay. The next bit is also 1. That is why it will be represented by half the bit duration positive pulse and next half the bit duration by negative pulse. Okay. So this Manchester code has built-in synchronization, means there will be transition in every bit, right? For half the bit duration, even for either binary data 0 or binary data 1, there will be a transition from positive amplitude to the negative amplitude, or from negative amplitude to the positive amplitude. That depends on what type of binary data is there, right? So this code is widely used and it is very much required also in many applications. Okay. Yeah, so this is just a recap what we can say. Already I discussed about this unipolar non-return to zero, what it is, right? So in this I said symbol 1 will be represented by a positive pulse, right? Having amplitude plus a volts, right? And symbol 0 will be represented by no pulse. Okay. And this unipolar non-return to zero, it is also known as on-off signaling. Okay, on-off signaling. So the drawback of this line code is there will be a waste of power. Okay, there will be waste of power due to transmission of the DC level. So if I have continuous zeros, right? So I said zeros will be represented by no pulse, right? So it is a constant value. Either I can have long sequence of zeros or long sequence of ones. So that leads to waste of power. So that is one drawback of this unipolar non-return to zero signaling. So this is about polar. I said in polar NRZ, a symbol 1 will be represented by what? Positive pulse, and symbol 0 will be represented by a negative pulse. Okay. And as far as the advantage of this line code is concerned, it is very easy to generate, okay, and it is more power efficient, okay, than the unipolar, because it has alternate means 0 represented by negative pulse and 1 will be represented by positive pulse, right? So there will be no DC component in this type of line code. Hence, we say this type of line code is more power efficient. Yeah, this is about unipolar return to 0. As I said already, 0 by no pulse and 1 will be represented by a positive pulse for half of the bit duration. Another half of the bit duration, it will come back to 0, right? So this type of line coding will be useful for bit timing recovery, okay, at the receiver side, because we could find the transition for every half the bit duration. So we can set at the receiver to recover the timing of the signal. Okay. So the disadvantage of this type of line coding is it requires 3 dB more power, okay, when compared to the polar return to zero signaling, okay, for the same probability of symbol error. Okay, as far as power consumption is concerned, by the use of this type of line code will be more when compared to polar return to zero signaling for the same probability of symbol error. So that is one drawback of this type of line coding. Okay, unipolar return to zero. And as I said, it will be used for bit recovery, bit timing recovery, right? How does it is possible? Because it has the delta function. Okay, I think the power spectral density of this line code, if we see, you'll understand. So there will be always a delta function, so which will be occurring at f equal to 0, f equal to plus or minus 1 by TV in the power spectrum of this line code. So that helps to use this line code as a bit timing recovery at the receiver side. Yeah, this is about bipolar return to 0. Uh, yeah, as I said, here 0 by 0 means binary 0 will be represented by no pulse, and 1 will be represented by alternate positive and negative pulses, right, with plus A and minus A amplitude. In that sense, we say it has 3 amplitude levels. Okay, so 0 by no pulse and ones will be represented by what? Alternate positive and negative pulses. Okay, since it is written to 0, so it will come back to 0 after half of the bit duration. Okay, so this line code has the property that it has no DC component. So that is the advantage. Okay, even polar signaling is also has a no DC component, and this bipolar return to 0, even non-return to 0 will also have no DC component. Okay. So that is why this line code is also known as alternate mark inversion, that is AMI signaling. And this line coding is used for error detection. Okay, because here in this type of line coding, we send a symbol 0 with no pulse and ones by alternate positive and negative pulses, right? So in the receiver side, we will be able to detect if any error in the transmitted signal by the use of this type of line code. So it has built-in error detection capability. Yeah, so this is what the representation of bipolar return to 0 line coding, right? So slightly this 0 has come this side. Actually, it should be 0 here, right? Then it is 1, next bit is 1, then 0, then 1, then 2 zeros, then next bit is 1. Yeah, Manchester code, I said a symbol 1 will be represented by a positive pulse, right? Symbol 1 will be represented by a positive pulse having amplitude A, and for half the bit duration, right? Then another half the bit duration, it will be represented by a negative pulse of amplitude minus A, right? So both the pulses will have the half symbol wide, means its duration will be half of the bit duration. And for symbol 0, it will be reverse, means half the bit duration it will be a negative pulse, another half the bit duration it will be a positive pulse. And this Manchester code also will not have any DC component. Okay. And as I said, this type of line coding will be very much used in many applications because it has inbuilt synchronization characteristics, right? Because we find every of the bit duration, there will be a transition from positive to negative or negative to positive. That depends on the type of binary data we transmit. So this is all about the various types of line codes. Yeah, this is what the representation of Manchester line code, right? 0 by negative pulse for half the bit duration, then another half the bit duration by positive pulse. Next one will be there, that is positive pulse for half the bit duration and a negative pulse for another half the bit duration. Then again, next one is there. So positive pulse for half the bit duration and again a negative pulse for the another half the bit duration. Next bit is 0. So negative pulse for half the bit duration, then positive pulse for another half the bit duration. Okay. The next bit is 1. So that will be represented by a positive pulse with amplitude plus A volts for half the bit duration. And next for another half the bit duration, it will be a negative pulse. Right. Next bit is 0. So that is why it is continued with negative pulse for half the bit duration. another half the bit duration will be a positive pulse. The next bit is 0, so it will be a negative pulse for half the bit duration, and another half the bit duration will be a positive pulse. So next bit is 1, so we represent half the bit duration by positive pulse, and next half the bit duration by a negative pulse. Okay. So I will give one example. You just try to draw, and you can post your drawing in the chat box. Okay. Take down the binary data 100 100 10 110. Exactly inverse of this data, whatever I have given here example, you can say I have taken inverse of this. Means I said 100, then 10110. Okay, so you start drawing all these four different types of line codes, starting from unipolar, polar, bipolar, and Manchester. I think you can draw for unipolar, polar, and bipolar, both return to 0 and non-return to 0. Okay. Anyhow, for Manchester, we don't say return to 0, non-return to 0, because for every half the bit duration, there will be a transition. Okay. So I will give 5 minutes. I think each and everyone should draw, and you should post your answer in the chat box. Then I will take up the next task. Yes, hope people have got my question. Whatever the example I have taken, I have given the inverse of that data. Okay, you need to draw the all those four different types of line codes. I said for first three, that is unipolar, polar, and bipolar, you draw both return to 0 and as well as non-return to 0. Then the last one is Manchester. Yes, is that fine? Yes, I'm asking people, is that fine?
Yes, sir.
So I hope you're able to see the slides now. I think you take exactly opposite of this. That is 100 10 110. And there will be one Paka question on this topic. Okay, they will give on 8-bit data. They will ask you to draw these different types of line codes.
Sir, done, sir.
Yes, Karunya. Skanda, can you present, man? Switch on your camera and present. Skanda.
Sir.
Yeah. Yes, Kuber. Manjunath. Manusri.
Sir,
Manjunath,
yes,
ಇವಾಗ ಮಾತಾಡ್ತಾ ಇದೆಯಲ್ವನ? Can you
sir.
present, man?
Yes,
Have you
sir.
done?
1 minute, sir.
Hmm.
Doing, sir.
Doing. Yes, what about Skanda? What happened?
Sir, ಅದು ಕ್ಯಾಮ್ರಾ ಆನ್ ಆಗಿಲ್ಲ ಸರ್, ವಾಟ್ಸಪ್ ಅಲ್ಲಿ ಕಳಿಸ್ಲಾ ಸರ್?
ಇಲ್ಲಿ ಚಾಟ್ ಬಾಕ್ಸ್ ಅಲ್ಲಿ ಹಾಕಲ್ವಾ?
ಚಾಟ್ ಬಾಕ್ಸ್ ಅಲ್ಲಿ
Yes, Kuber. Ramya. Ramya, you Kashyap.
Just a minute, sir.
Okay. What about Rakshita? Harshita? Yes, Sudiksha. Yes, Mohan Sai. Yes, Ramya, is it possible to present or is it possible to put it in chat box?
Sir, I'll show it, sir. One
You
minute.
can present. Switch on your camera and present.
Yes, sir. Yes, sir. 1 minute, sir.
Yeah. Yes, Ananta. Ananta.
Yes, sir.
ಏನ್ ಮಾಡ್ತಾ ಇದೀಯಾ? ಮಾಡಿದ್ಯಾ ಲೈನ್ ಕೋಡಿಂಗ್?
Doing it, sir.
ಸರ್ ವಾಟ್ಸಪ್ ಅಲ್ಲಿ ಕಳ್ಸಿದೀನಿ ಸರ್ ಅದನ್ನ.
ವಾಟ್ಸಪ್ ಅಲ್ಲಿ ಕಳಿಸಿದ್ಯಾ? Yeah, similarly other students also. See, I am asking so many, but they are responding very slowly. Hmm? You should, Skanda, you should mention the bit duration. Okay, you write TB, then for return to 0, it should be exactly half of the bit duration. It should be, it should come back to half of the bit duration from high to low.
Yes, sir. Yes, sir.
Yeah, you write x-axis is time and then mention the bit duration. I think that is fine. Bipolar NRZ you have not written.
Sir, ಬರ್ದಿದ್ದೀನಲ್ಲ sir. Polar NRZ.
Bipolar return to 0 ಬರ್ದಿದೆ. Bipolar NRZ ಬರ್ದಿಲ್ಲ. Polar ಬರ್ದಿದೆಯಾ NRZ? ಯೂನಿಪೋಲಾರ್ ಎರಡು ಬರ್ದಿದ್ಯಾ NRZ ಮತ್ತು RZ. Polar NRZ ಬರ್ದಿಯಾ? Bipolar RZ ಬರ್ದಿಯಾ? Then Manchester.
ಬರಿತೀನಿ sir, ಬರಿತೀನಿ.
Hope able to see my whiteboard.
Oh, yes, sir.
Okay, let me draw from my side. Yeah, let me draw that 8-bit data. Okay, that is 1. Next is 0. Next is also 0. Right? Then 1, 0, 1, 1, then 0. Okay, so this is my 8-bit data. I asked you people to draw various line codings, right? Okay, first let me should draw this vertical line so that you can mention what is the bit duration. Okay, first let me write unipolar NRZ. Unipolar NRZ, right? Now return to 0. Unipolar, what I said, in unipolar, 0 will be represented by no pulse, 1 will be represented by a positive pulse having amplitude plus A volts. So first bit is 1, I can represent by a positive pulse, right, with amplitude 1 plus A volts. Next two bits are 0, 0, so I write 0, 0, no pulse. The next bit is 1, so represented by a pulse having amplitude plus A volts. So it is NRZ, so it will be occupying the entire bit duration. So next bit is 0, no pulse. The next bit is 1, by positive pulse. Right? Next bit is also 1. I can continue with the positive pulse. And next bit is 0. Okay. And you can say this is your bit duration TB. Similarly, unipolar return to 0. Okay. Unipolar return to 0. What I said in case of unipolar return to 0. So one will be represented by a positive pulse for half of the bit duration. For another half the bit duration, it comes back to 0. Okay. So this is TB by 2. So this is my 0th value. Okay. And this is 0. So next bit is 0. So it will be no pulse. Next bit is also 0, no pulse. So next bit is 1. So it will be plus A volts for half the bit duration. And again it comes back to 0. Okay. It should be on this line. So next bit is 0. Right, no pulse. So next bit is 1. So half the bit duration will be high. And then comes back to 0. So next bit is 1. So it will be high for half the bit duration, again it comes back to 0. Next bit is 0. Right? So this is what return to 0 is. Okay. Then is polar. Polar NRZ, let me read first. Polar NRZ. So in polar NRZ, I said plus A, then minus A. Right? In polar, symbol 1 will be represented by positive pulse and symbol 0 will be represented by a negative pulse. So first bit is 1. So I represent that by a positive pulse. Okay. So next bit is 1. That will be represented by a negative pulse. The next bit is also 1. It will be represented by a negative pulse. Right? And next bit is 1. So it will be represented by a positive pulse. So it will occupy the entire bit duration. That is why it is written full duration. Next is 0. Right? Next two bits are 1, 1. And next bit is 0. Like this. Okay. Then polar return to 0. Polar return to 0 will be what? 0. Then A. Then this will be minus A, right? So in case of return to 0, as I said, it will be high only for half of the bit duration. Right? Then it will come back to 0. So this is polar return to 0. Okay. Then next bit is 0. So it will be a negative pulse for half the bit duration. Again, it comes back to 0. So next bit is also 0. It will be negative for half the bit duration, comes back to 0. So next bit is 1. So it will be high for half the bit duration, comes back to 0. The next bit is 0. So it will be negative pulse for half the bit duration, comes back to 0. So next bit is 1. So it will be positive for half the bit duration, comes back to 0. So next bit is also 1. It will be high for half the bit duration, comes back to 0. So next bit is 0. It will be negative for half the bit duration, comes back to 0. Yes, is this fine? Yeah, this is about unipolar and polar. Similar to that, I think we can draw other things also. So this seems to be very easy, but only when you start writing, you will understand. Okay. Looking at this, okay, I can write, but many people do mistake with that confidence only. That is why I started drawing on this whiteboard. Okay. Otherwise, I would have gone with the PPT only. So let me take bipolar now. Okay. Bipolar NRZ. Okay. So I said it has 3 values plus A, minus and 0. So first bit is 1. Since it is NRZ, right? So I represent by a positive pulse. Okay. Next two bits are 0, 0, no pulse. Right. So next bit is 1. So that will be represented by a negative pulse. Right. And because the previous bit is represented by positive pulse, so next coming one will be represented by a negative pulse. Right. Next is what? It is 0, no? Next bit is 0, no pulse. So next two bits are 1, 1. So it will be one bit will be represented by a positive pulse. Okay, because the previous one is by negative pulse, right? So now the next bit will be represented by a negative pulse. That is 0. So this is what bipolar NRZ. Similarly, to draw bipolar return to 0, okay, you can say 0, A, minus A. So return to 0 means what I said, it will be high for half the bit duration, it comes back to 0. So next is 0 only, no pulse. All right, next is 0, no pulse. Next is 1. So it will be negative for half the bit duration, comes back to 0. So next bit is 1. So it will be high for half the bit duration, comes back to 0. So next bit is 1. So it will be negative, comes back to 0. Then 0. So this is what bipolar return to 0 is. So then Manchester.
So can you explain bipolar non-return to 0 again, sir?
Yeah, I will look. Yeah, in case of bipolar, whether it is return to 0 or non-return 0, so 0 will be represented by no pulse. Okay, 1 will be represented by alternate positive or negative pulses. Means I have first 1, right? So that is represented by a positive pulse. Next I have two zeros represented by no pulse. Next 1 is there, right? So now I will be representing that by a negative pulse because the previous one was represented by a positive pulse. So 1 will be representing alternatively by positive and negative pulses. Is this fine?
Yes, sir. Yes, sir. Got
Yeah.
it.
And the next bit is 0, there will be no pulse. Next two ones are there. So the previous one was represented by a negative pulse. That is why here I am representing by positive pulse. Okay, positive pulse. And next one will be represented by a negative pulse. So data 1 will be represented by alternate positive or negative pulses. Sir. Okay, so let me draw Manchester code. And with that I can. Yeah. So Manchester code, I said what? First bit is 1. So half of the bit duration it will be represented by a positive pulse, and another half the bit duration will be represented by a negative pulse. Okay. So this is TB by 2. Then next bit is 0. So there half the bit duration will be represented by a negative pulse. Then another half of the bit duration will be represented by a positive pulse. Right? So what is next bit? Is 0, right? So next bit is 0. So half the bit duration will be represented by a negative pulse. Then another half the bit duration will be represented by a positive pulse. Next bit is 1. So half the bit duration will be a positive pulse. Another half the bit duration will be a negative pulse. And I hope, what is the next bit? After 1 it is 0, right? So it will be represented by a negative pulse for half the bit duration and another half the bit duration by a positive pulse. So next bit is 1. So it will be represented by a positive pulse for half the bit duration, then another half the bit duration by a negative pulse. Right? So next bit is 1. So it will be represented by positive pulse for half the bit duration another half the bit duration by negative pulse. So next bit is 0. So it will be represented by a negative pulse for half the bit duration, and another half the bit duration will be positive pulse. So this is Manchester coding. Manchester code, or it is also known as split phase. Okay. Hope this is clear.
Sir,
Yeah.
sir, I have a doubt in Manchester coding.
Yeah. Tell me, what is your doubt?
Sir, 100 and 1, the fourth
Ah.
fourth bit.
This is first bit is 1. Next is 2 zeros. Right.
Yeah, sir.
Then 1 is there. Then 0 is there, right? Then 1, 1, 0. Yeah. Tell me, what is your doubt? I said 1 will be represented by a positive pulse for half the bit duration. Okay, another half the bit duration by negative pulse. Then 0 is there. So half the bit duration by positive pulse, another half the bit duration by negative pulse, another half the bit duration by positive pulse. So next bit is also 0. So that is why I represent by half the bit duration by negative pulse, another half the
Sir,
bit duration
should
by positive pulse.
all can't they be continuous? Like after 0, you can continue.
See, it is a 0, man. Here 0, right? So I need to represent that by half the bit duration by negative pulse, right? Then another half the bit duration by positive pulse. So for every half the bit duration, there will be a transition. There is a Manchester code.
Yes,
So
sir.
you are expecting this should be continued for negative only, right?
No. After 0, 0, you start 0, no? First half will be negative, next half will be positive.
Yeah.
Again, there
Yeah.
is a 0, no, sir. So can't we do
That
like
is right. Yeah, that is right. See, first 0 for half the bit duration negative pulse, another half the bit duration by positive pulse, right? So next
yes,
0
sir.
is there, right? Again, we have to start with negative pulse for half the bit duration, then another half the bit duration by positive pulse.
Yes, sir.
For 1 also. See, for half the bit duration by positive pulse, another half the bit duration by negative pulse. Next one is there, half the bit duration positive pulse, another half the bit duration by negative pulse. So for every half of the bit duration, there will be a transition from positive to negative or negative to positive depending upon the binary data. So that is the beauty of the Manchester code. Okay, that is why we say it has a self synchronization clock. Means I will be able to identify for every half the bit duration when the transition takes place. So depending upon that, I can decide whether the data is 1 or 0. Okay. Okay, so hope you are able to see my PPT.
Yes, sir.
Yeah. So next one is the differential coding. Okay. So what is happening in differential coding is okay, this method is used to encode the information in terms of signal transitions. Okay. So here the transition is used to designate symbol 0 in the incoming binary data stream, and no transition is used to designate symbol 1. Okay. So whenever the transition takes place, that will be designated by symbol 0, and whenever there is no transition, that will be designated by symbol 1. So let us see how do we do this. Okay. So this is the example what I have taken. So this is my original data, that is 0, 1, 1, 0, 1, 0, 1. This is my original binary data. And how do I do that differential encoding? Okay. So for that I take the reference bit. Okay, this is my initial bit. Okay. This initial bit or the reference bit can be taken either 0 or 1. So here I have taken 1. Then what I do, that encoding is, I XOR these two bits. XOR of these two. Okay, 1 XOR with 0 is what? Yeah, I said this is my original data, right? Original binary data. and this is my differentially encoded data. I said I take the initial bit or reference bit, either I can take it as 1 or 0. Here I have taken 1. Okay, then I do, as I said, XNOR operation. XNOR. Okay, 1, 0. Right, so they are at different levels, right? So what will be the resulting signal? It will be 0. Right, XNOR. Then next is 0, 1. These two bits I am ignoring. Then it will be 0, right? Because they are at different level. Then 0, 1, it's 0 only, right? Then 0, 0. So they are at the same level, the output will be high. Hope you're understanding what I'm saying. I do the XNOR operation. Differential encoding is nothing but XNOR operation. Okay? XNOR of original data with the initial taking reference bit as 1. So XNOR of these two, 1, 0, it will be 0, then 0, 1, it will be 0, then 0, 1, it will be 0, 0, 0, it will be 1. Next is 1, 1 is there, so it will be 1, right? Then 1, 0, it will be 0, right? Then 0, 0, it will be 1, right? Then 1, 1, it will be 1. So as I said, the transition takes place at symbol 0, right? No transition means symbol 1. So I taken reference bit as 1, right? Next bit is 0, so transition taken from high to low, right? Next bit is 0, next bit is also 0, so it is at the same level, right? Next is 1, so transition is taking place, so it is at the same level for another 2 bits. Next is 0, again transition taking place from high to low, okay? Transition is taken from high to low. So next is 1, so it is at high level. So this is what a differential encoding is. Hope this point is clear. Take the original binary data, right? Take the initial reference bit as 1. Either you can take it as 1 or you can take it as 0. If you take it as 0, you'll get opposite of this code. Okay. Then do the XNOR operation. So that will be our differentially encoded data. So what is the advantage and all we'll see. Okay. Okay, so I think with this I will stop today. So let me discuss further in the next class.